Okay, now that we've established what a vector space is more generally, we can talk about what a subspace is more generally. Back in section 5.1, let me just make sure that is really where we talked about that. Yes, in 5.1, we had this theorem 5.1.2 called subspace criterion. And the definition of a subspace is here, and these are the criteria that had to be met. Criteria, by the way, I think is a misnomer. It should be criteria. Your book says criterion. Criteria. Criterion is singular. Criterion is singular. Criteria is plural. So there are 3 criteria. I'm an English minor, so humor me a little bit here. Anyway, the definition of a subspace is that a subspace called W of Rn is just a subset of Rn, but it also has to form a vector space itself. So W has to be a vector space, and if it's a vector space in its own right, and it's a subset of Rn, then we say it's a subspace of Rn. Okay, that's back from chapter 5 when we were only talking about real number vectors in vector spaces that are comprised completely of real number vectors. We didn't have any of this other stuff back then. The criteria we had to meet back then were that the 0 vector was in the subset, right? Letting W be a subset of Rn, then the 0 vector had to be in that subset. In other words, you could take any collection, smaller collection of vectors out of Rn, and as long as that collection contained the 0 vector, some collections would not, but the ones that did were candidates for being subspaces, right? If they don't contain the 0 vector, they're zero vector. If they don't contain the 0 vector, then they're not even candidates to be subspaces. They're still subsets, but they're not subspaces. Once you've established that the 0 vector is in the subset, you have to check to see whether the subset is closed under addition and closed under scalar multiplication. And back in real number vector land, what that looked like was that if I had a u and a v, 2 vectors in W, then u plus v was also in W. And scalar multiplication, same thing. If A was a real number and u is a vector in W, then AU was also in W. So if I add 2 vectors in W together and they land back in W, then we say W is closed under addition. That was the operation that I did here. We say that W is closed under scalar multiplication if I scale the vector U, multiply it by A, and the result lands back in W. Okay, so those are the 3 things we need to check if we have a collection of vectors and we want to know if the vectors in that particular collection are a subspace of some other vector space. We first need to check that those vectors came from the vector space. In other words, that they form a subset of the vector space. Then we need to check that the 0 vector is in here in the subset. We need to check that vectors in the subset are closed under addition and scalar multiplication. If all 3 of those requirements are met, then we say that W is a subspace of Rn. Now, in the greater world of vector spaces that we know now, we need to make some changes to this before we can apply it to vector spaces that are not necessarily real number vectors. First of all, this isn't Theorem 5.1.2 anymore. The number doesn't matter. I can name a theorem anything I want, or number a theorem anything I want. What's really important is the name, because that tells us what's being discussed in that theorem. But it's still called the subspace criterion, or if I were to rename it, the subspace criteria theorem. And here what we're going to do, the thing that we're going to do differently, is we're going to let W be a subset of a vector space V. I'm going to say, how do I want to do this? I want to specify that. So I'm going to say a subset of vector space V. Okay, then, if that's true, then W is a subspace of V if and only if the following criteria are met. Now, here we have to be very careful. We can't just cross out a few things and change them a little bit, because we need a zero vector in W, but it might not be a zero. It might be a matrix of all zeros. It might be 0 plus 0i if our vector space is the complex numbers. It could be any number of things, not necessarily what we would recognize as a zero vector. So what we're going to say instead here, I think what I'll do is rewrite number 1 down here. We need something that will act like a zero. And what we call zero when we're working in the real numbers is the additive identity. It's the thing you can add to any number and get the same number back. So I'm going to say that the additive identity is in our subset. Additive. Okay, and that's the equivalent in the bigger vector space of saying that the zero vector, right? The zero vector in real number vectors is the additive identity. It's the vector you can add to anything and get the anything, whatever you added it to, you'll get that same vector back. In the real numbers, we just call that the number zero. The additive identity is the number zero. In the greater world of vector spaces, we have to call it the additive identity because we don't have a single formation of how what that might look like. It'll depend on the vector space that you're working in, but it does have to exist. The additive identity has to be in there. If it's in there, if that's in there, then W, actually I'll write it this way. And therefore, this means therefore in math abbreviation speak, therefore W is non-empty. Right? We know there's at least one element in that subset, and it's called the additive identity. Okay, and then number 2, the way your textbook has it written, is a combination, I think, that's how I'm reading it, of two Roman numerals 2 and 3 in the above, in the old version, right? In the real number vector version. It says if U and V are in W. Now, U and V are still vectors. We just don't know whether they look like real number vectors or matrices or polynomials or something else. U and V are in our subspace, in our subset, right? We pull these from the subset. And then we can, I also need A and B are in F, the field F. Let me write field. Field F. Put an ampersand in here as well because I need both. Then AU plus BB is in W. And what this means is that I've scaled and added. Now, A can be the multiplicative identity, right? If A is the multiplicative identity in whatever the field is that I'm working with, then that's like saying 1 times U. So I get just U plus V. In that case, U plus V, and if B is the multiplicative identity as well, U plus V is in W. Right, so that's equivalent of saying that W is closed under addition. If either U or V is the additive identity in W, then I get AU, if V is the additive identity, that's effectively saying 0. V times 0 is 0. I get AU is in W. And if both of those are true, then it's W is closed under addition and W is closed under scalar multiplication. So those are both encapsulated in this one statement. The other thing I need to add to my this version of the subspace criteria theorem is that down here I specified a field F, and up here I did not. So what I've got here is that W is a subset of the vector space V, and I need to add, tidy this up just a little bit, the vector space V over a field F. So that needs to be part of my statement, right? W is a subset of the vector space V over a field F. The field is important. Now, I don't know what that field is, but I do know that's where A and B come from. That's where we're drawing our scalars from. Let's take a look at an example of how you might try to find out whether a subset of a vector space was a subspace of that vector space. Okay, so here's our example. Let W be the set of all 2 by 2 symmetric matrices. We're going to find out from what follows whether W is a subspace of 2 by 2, of M 2 by 2. The first question you really need to ask yourself is W a subset of the M 2 by 2 vector space? And the answer is yes, because this vector space consists of all 2 by 2 matrices, A, B, C, D, where A, B, C, and D come from the real numbers. Okay, so that's all 2 by 2 matrices. 2 by 2 symmetric matrices are only different, are only particular, if you will, in that instead of having potentially different numbers here, those numbers must be the same, because symmetric matrix is one that's equal to its own transpose. So let's call that number K, and I think I'll use green, why not? Now if I take the transpose of this matrix, I'll get AK as a row here is good grief, I keep picking the wrong pencil, is AK as a column, and KD becomes, KD as a row becomes KD as a column. And these two things are the same, right? So this matrix is equal to its transpose, and so therefore this matrix is a symmetric matrix. Because it's a symmetric matrix, we can say that it is an element in M 2 by 2. Because it's an element of M 2 by 2, no matter what A, D, and K are, as long as these two numbers are the same, we know that W is a subset, right? All of the matrices that look like this are the ones that make up W, but they are all also in M 2 by 2. So W is a subset. So that's our first kind of test. It's not one of the criteria, but it's a critical piece of information. It's not one of the listed criteria, but it is an important piece. Now we need to check and make sure that it's non-empty. To be non-empty, there just needs to be one such matrix. And for example, I could use 1, 0, 0, 1. That matrix is it's in M 2 by 2 because it's a 2 by 2 matrix, and it's in W because it's symmetric. These two values are the same. These two values also happen to be the same, but it doesn't matter. I have found something that exists in the collection of symmetric matrices. So it's a non-empty space. It's a non-empty collection. So we have satisfied this criteria here. We've satisfied the requirement that the subset, first of all, is a subset, and that subset is non-empty. The additive identity is another element in this subset, and that is sufficient to show also that W is non-empty. The additive identity of 2 by 2 matrices would be all zeros, and because these two numbers are the same, regardless of what these two numbers are, this is a symmetric matrix, therefore it is in W, the set of all 2 by 2 symmetric matrices. So this element is also in W. This is the critical one, but it turns out that really all we need to show is that W is non-empty. So either one of these would do. So we've checked that criterion, and the next one is to check whether W is closed under addition and scalar multiplication. Now we haven't specified here, so we're going to say W is a subspace over the real numbers because we haven't said otherwise. So I need to check whether, let's let A and B come from the real numbers and check whether A times a vector u in W plus B times a vector v in W turns out to be also in W. This is what we're trying to determine. So let's take a look at that. We also have that all the values inside the matrix are from the real numbers as well. So I'm going to make up a couple of matrices. Let's call them A, B, B, C. Remember, these are symmetric matrices, so these two numbers have to be the same. And I'm going to erase more here. Doesn't really quite apply anymore anyway. And let's use D, K, K, M. Again, as long as these two numbers are the same, it doesn't matter what these two numbers are, as long as they're in the real numbers, because that's where this kind of vector lives. And then these two have to be the same because we're in W, so we're checking these criteria for W, 2 by 2 symmetric matrices. And then I want to take two real numbers, let's call them P and Q, and multiply those matrices. I said Q and I wrote D. I already have a D, so I'm going to go ahead and change that to Q. Multiply each matrix by its respective real number, scalar, and check to see what the result is. I'm going to have to write really small down here. I'm going to have PA plus QD for my first entry, because I'm multiplying P by all four of these entries, Q by all four of these entries, and then I'm taking the resulting entry from PA and adding it to the resulting entry from QD, and that ends up in the same position. So I'm going to have a matrix that looks like this, where my first entry is PA plus QD. My second entry is going to be PB plus QK. My third entry is also going to be PB plus QK, PB plus QK. My last entry will be PC plus QM. My resulting matrix has four entries. It's a 2 by 2 matrix, so it satisfies that it belongs in M22. It's a different color. It belongs in M22. It also belongs in W, because these two entries, this one right here, let me highlight these. It's a little harder to see. These two entries here are the same, right? They're made up of the same sum and product of real numbers. They're going to result in the same numbers. So they're also in W, and I've checked both scalar multiplication and addition at the same time. So yes, in fact, AU plus BV for any A and B and any U and V is also in W. So that means that W is a subspace of M 2 by 2 over the real numbers. I took this example from a different textbook. Your textbook does this exact same problem in example 6.2.3, but it defines a subset of R 2 by 2 as a collection of vectors A, B, C, D, 2 by 2 matrices, A, B, C, D, where B and C are equal. So I'll go up here. It says A, B, C, D, but make sure that B and C are the same number. And that's what we're calling a symmetric matrix. Your textbook does this example. It just goes about defining it as kind of on the fly. It doesn't define symmetric matrices. It defines the properties required to basically to do the problem. So that is example 6.2.3, a slightly different way.